Hey everyone. Today we're going to code a neural network from scratch. The type of neural network we'll be creating is called an MLP, which is multi-layer perceptron. There are multiple different types of neural networks. Each one is suited better for different types of inputs and different outputs. This specific one works well for classification problems, such as um, you have a picture of something and you need to identify what it is. So a good example of this is the MNIST dataset where it has handwritten digits and it's trying to guess what the digit is. So it might be a handwritten 4 and then at the end of it it says this is a 4. Another good data set for this is the Google Quick Draw dataset where it has hand-drawn images of things. So one might be a rocket, one might be a dog, another one might be a bicycle, and it sends it through and you take the data from that image, and at the end of it, it says, I think this is a bicycle, or I think this is a rocket. So let's go ahead and start coding. But before we start coding, let's talk about exactly what we need. So the first thing we're going to need is a model class. And the model class is going to be a class that houses the layers themselves. And at the end of this, we'll write some logic to actually save this model. And then that way you can load the model later and you won't have to retrain it. It will remember all of the layers and each layer has its weight and biases and so on. Which brings us to our next part. We'll need a class for our layer itself. So each layer is going to have multiple neurons or nodes. So we need a class that will house those, as well as the weights and biases for each. It'll also have some logic to, when we're moving forward through the neural network, do the calculations to make guesses, as well as we'll have some logic that as we're doing back propagation, meaning we work backwards through the neural network to correct any mistakes that we made, we'll have some logic for that. The next thing is we'll have training logic. So after we're done with all of this, we'll want to take a chunk of our data set and we'll want to give it images of like a handwritten 4, and then we'll say, guess which digit this is. And at the end of it, it says, I think this is a 5, and we'll say no, and then we'll do some calculation. We'll say, here's how wrong you were, and it will go backwards, and then it will try again with these new calculations or these new weight and biases. And at the end of it, after multiple iterations of that, it should have all of the weights and biases and the layers and nodes should be configured to make this prediction correctly. So that logic will just actually go through, make those adjustments, and run everything. The next thing we'll need is activation logic. And in a neural network, what activation logic is as we work through this neural network, as we work through layer by layer, node by node, we're going to need some logic to say, I'm very far off or I'm not far off. And what we can actually do is we can actually say, if we get to a node and we see that it's making a really bad calculation, we're just going to say, you know what, I'm going to deactivate this. I'm going to still move forward, but I'm going to move forward as if I never made this calculation. So instead of me passing the output of my calculation, I'm just going to pass a 0. Because what's going to happen is after that, the 0 times anything is 0, so it's just going to null out the output of a node. And then we'll need some loss calculation logic. Going back to our training, what we'll need is some sort of logic to take our incorrect guess and say, how incorrect were we? It's not enough to say that we were correct or not incorrect. Were we way off or were we very close? And what it'll do is it'll actually give us a number that's a decimal that's between 0 and 1. And then that way we can kind of put everything on the same scale of like how close or far off were we. And the next is we'll need inference logic. And what inference logic is just after we're done with this, I want to give it an image, either the image of a handwritten digit, or I want to give it that hand-drawn like a rocket ship and have it correctly identify it. So just after we're done with our model, let's actually make a prediction with it. So the first thing we're going to work on is the layer class itself. So for that, we'll go ahead and start a new class called dense layer.python. And the reason we're calling it dense layer is in a neural network, a dense layer is one where every neuron in it is connected to every neuron in the layer before it and the layer after it. So if we have 5 neurons in this layer and we have 5 neurons in the next layer, every neuron is connected to every one of the 5 after it, and then every one of those is connected to every neuron in this layer. So first, let's go ahead and import NumPy. The next thing we'll do, we'll go ahead and create our class. And for the first go around, we're going to just create all the functions. So we're going to create a constructor, a forward function, and then a backward function. And then we'll go back through and actually fill those in because we may need to actually do some other logic before they're usable. So first we'll create the constructor. And since it's a class, we're going to first pass self always. So the first thing we're going to pass in is the input size, and the next thing will be the output size. So the input size is going to be the number of nodes that's in the previous layer, and so the input size will be the number of nodes or neurons in the previous layer, and the output size will be the number of nodes or neurons in the next layer. And so the next thing we're going to do is we want to initialize weights. So we're going to do a calculation here in a second, but first I just want to get through it. I want to just declare the variable, and we'll come back and set something for it after. And the next thing I want to do is declare the biases. So again, we're just going to not worry about that for now. We're just going to declare it as none. And then the next thing we want is we want to store our input every time we run through, and then our output. We're going to set these as none or null, but these are actually going to stay as none or null because when we go to do the forward logic after and the backward logic, that's when they will actually get set. So the first thing is let's go ahead and set our weights. So the first thing we're going to want to do is we're going to make a random, we're going to make a matrix then, and the shape of this is going to be the output size times the input size, or output size by the input size. And the reason for that is we want the weights to be for every input, we want a weight for the output. And then the next thing we're going to go ahead through is we're going to multiply all of those because we are setting random values, but we want them really random. So we're going to go ahead and do 2 divided by input size. So we're going to do the square root of 2 divided by input size, and then that will at least anchor our, even though they're random values, it'll kind of adjust them relative to our input size. The next thing we're going to do, we're going to set our biases, and for now we're just going to have no bias. We're just going to assume that there's just none. We'll let those adjust themselves later. And the shape of that, we just want the output size by 1 because we just want 1 bias for every output that we're going to give. So the next thing we're going to do is we're going to create a function for forward. We're not going to code the inner workings of this just yet. We have actually some other things to code before we get to it. But right now we're just going to go ahead and get the shape of it there. And then that way we have it and we can always return to it after. And just for reference, forward is when we're working through the neural network forward and we're making calculations in an attempt to guess, we're going to go through each node and each layer forward from the input working towards the output. But now we have backward, and what backward is what we call backpropagation, and that is after we've made a I'll wait for this. After we've made a prediction, we're going to do a calculation to say how right or wrong were we, and then using that prediction or that value that we get of how right or wrong we were, we're actually going to work backwards through all the calculations we did. So we're going to start at that output and we're going to work backwards through the layers from the output layer all the way back to the input. And for each one, we're going to figure out where it went wrong. We're going to do some calculation of, okay, if it's wrong, how wrong was it? And out of all of the nodes in this layer, which ones were more wrong than others? And using that, we can make adjustments. The idea would be if you had a classroom full of students and a teacher asked a question and everyone shouted out an answer. Um, and the teacher said, I got my answer wrong because I listened to the collective of the class. So I'm going to go through and say, okay, you got the answer really, really wrong. So I'm going to have you like maybe not shout as loud. And then you got the answer right. So maybe you shout a little louder. And that's kind of the idea behind the weights and biases, is we want to kind of bring up the answers that are closest to the correct and then kind of suppress the ones that are farthest from the correct answer. And then with each of those, which each pass through, we kind of move a little bit in one way or another. And then the end of it is we get all of these nodes that are really close to the right answer, or they have at least the kind of gates and logic to kind of figure out the right answer. So as we work backwards, so we're going to say we're going to have an input of an output gradient. And what this is the output gradient is, I'd mentioned that we're going to do some calculation of how wrong the answer was. So we're going to do that how wrong calculation that each node in the layer before this was, and some logic is going to be done to that, and then it's going to be passed to the layer behind it. So when the backward propagation, we're going to take that and as well as a learning rate, and we're going to do some calculations on it. We're going to adjust weights, biases, get a new output gradient, and then we're going to use that, and we're actually going to pass that backward again, in which case we would hit the next layer. So before we can begin to code the forward and the backward logic, we're actually missing some logic that we need to fill in, and that's specifically the activation logic. So we'll go ahead and create a new file, and we'll just call it activation.py. And we'll go ahead and save this first. And for the activation logic, we're going to use something called ReLU for an activation function. There's several that you can use. You can use like ReLU. You can use sigmoid. There's another one that's called leaky ReLU, which is kind of like ReLU, but it's a slight adjustment on it to fix some of the downsides. We're not necessarily worried about that for this case. We're just going to use ReLU as it is. Yeah, so we'll go ahead and first of all, we'll make two functions, and we're just going to call it ReLU. And then we're just going to take an input of x, and then for now we'll just return. We'll code this after. And then the next one is going to be called ReLU derivative. And again, we're just going to take x, and then we're going to return, and then we'll code this in a second. So the idea behind these is when we go forward, we want to do some calculation to say, like, we've gotten to this part, we've done a calculation, we have an output, and we need to make a decision. Do we feel like this is a good enough output to move it forward and actually pass this answer on to the next person or onto the next layer? Or is it kind of a bad answer and let's just not even pass it through? So that's what the ReLU part is. And then the derivative is going to be when we do back propagation. we're going to do a calculation to just say, basically if on our pass forward we did give an answer, when we work backwards, we want to make sure that we're only passing backwards the ones where that node was activated. So if the node wasn't activated, we're just going to zero out also what we're passing backwards. And the way this works, so first, let's go ahead and import NumPy. Yeah, so the way this works is really, really simple logic. We basically want to say if it's if it's 0 or a negative number, we want 0. And if it's a positive number, we want the positive number. So we're going to say b.maximum, and we'll just say we want x or 0. And then, so we're basically saying like, and we can leave a comment in here just to make it clear, if value is less than or equal to 0, turn 0, else use the value. And the reason why this is important is because we're going to pass a 0, because when the next layer goes to use this number, if we pass a 0, because we are deactivating this node, the 0 times anything is 0, so it'll actually cause a 0 down the line. And then the derivative is kind of the same idea, except for the idea is that when we pass it, we want to say if x is less than 0, less than equal to 0. I mean, I guess it doesn't matter. If x is less than 0, we want 0, else 1. Actually, let me flip that, because I'll say if x is more than 0, we want 1, otherwise 0. And the idea here is the same thing. We just want to know when we work our way backwards, we're just going to pass in what we originally had for the outputs, and we're just going to say like, okay, we did use this, so let's activate it, or let's just put a 1 as like a binary like we did deactivate it, or we're going to say, okay, we didn't use this, so all we want back is a 0. So now what we can do is we can go ahead and code our forward. And for that, we're going to go ahead and say from activation import, and we'll import ReLU and ReLU derivative. Again, ReLU is going to be used for the forward, and then ReLU derivative is going to be used for the backward. So the forward logic is going to be actually pretty easy in this one. Let's go ahead over here, and the forward logic is going to be pretty easy. So the first thing I want to do is we're going to set the input on the class itself to be the input data. We're setting this because, oh, whoops, I've got an equal sign. We're setting this here in the class so that as we do backpropagation, we still have a copy of the input data. And then the next thing we're going to do is we're going to do matrix multiplication. So we want to take our weights that we have, and we'll say raw output, and we want to do some matrix multiplication. And there's some good videos out there on matrix multiplication if you don't understand it. But basically we want to take two multi-dimensional arrays and multiply them together to get a product of the both. And what we want to do is we want our weights. So we want to multiply our weights by the input data. Basically, we have all these different weights, and we want to put it against our inputs that are from the previous layer. And then also what we want to do from there is we want to add our biases. So we want to take our weights, and we'll do a matrix multiplication, which will result in a matrix. And then we're going to do plus the biases for this layer. And when you do with a NumPy array or a NumPy like a matrix, when you do a plus a integer or a float or some static number, what it's going to do is it's just going to add this to everything in the matrix. So what we really have is a situation where we have our input numbers coming from our previous layer, and then we have our weights. And what we want is for all of our weights, if it's a small weight, it's just going to adjust that input just a little bit. And then if it's a big weight, it's going to adjust it a lot. And that's our way of kind of like when we do the backpropagation and we tweak our weights and our biases, it's our way of tweaking how much we want to change the calculation on this neuron in each one. And then the biases is very similar, except for instead of it being multiple, what it ends up being is just kind of adjusting it left or right. So it's like a plus or a minus. So then the next one is the activation function. We'll actually spread these out just to make them a little bit easier. So the next thing we want to know is we're going to set our output to the result of the activation function. And for that, we're just going to pass in the raw output. And if you're wondering why we don't just return the output function, instead we're setting it here and then we're going to return it, it's because when we, in this instance of this class, this dense layer class, we're going to go forward, and then we're going to come back and we're going to go backward. And when we go backward, we're going to want a copy of the outputs from the last time we went through. And that is our forward function. And one thing I did skip over is we have our activation function. And what this will end up being is, so in times when it does this matrix multiplication, when we have negative numbers or zeros, for those places in the matrix, we're just going to have a 0. So we're essentially deactivating the node that is associated with that matrix. Because if you remember, the matrix that is weights, and all of that is going to end up being the output size times the input size. And then if it is good, like if it is above 0, we're just going to give the value itself. Now we'll move on to coding the backward function. And this is the function that's going to handle the logic during backpropagation. And a reminder what backpropagation is we're going to work through our neural network and we're going to make a prediction. And at the end of it, we're going to get a score from 0 to 1. The closer we are to the correct answer, the closer it will be to 1. And the farther we are away from the right answer, the closer we'll be to 0. So we'll get a kind of a gradient of 0 to 1 of basically how right or how wrong are we. And we're going to use this to figure out how much to change the weights and biases as we work backwards. The idea being if we're really wrong, we want to make big changes. We're not even close, so make a big change and try something completely new. If we're a little wrong, like we're close, but we don't quite have it, we don't want to make a big change because we're almost there. We don't want to, move way away from the right answer. We want to make a small change and just kind of like try to get a little closer to the right answer. And then with that, we'll start talking about the arguments here that are passed in. So we have the output gradient, and what that is that is going to be the scoring of the next layer. So in this case, we're working backwards. So if when we were working forward, the layer after this would have an output gradient, that basically that score of how right or wrong was each neuron. And then we have a learning rate, and a learning rate is kind of an adjustment multiplier of how much do we want to make a move. So we mentioned that with each time backwards through, we're going to make some sort of an adjustment. Do we want to take big steps and make big adjustments, or do we want to make small adjustments and so on? And you can think about this if you were playing, hide and seek, and you were doing hot and cold, where somebody says, "Oh, you're getting warmer, warmer, you're almost there, warmer," and then you take a step left, and somebody says, "Oh, nope, you're getting colder," and so on. So let's say you're taking big steps. You want to do big learning rate. So you might take a giant step, a big step, and it'll say, "Oh, you're getting warmer, you're getting warmer." And you might take a big step and you'll actually step past where the person that was hiding was, if you're playing hide and seek. And it's going to say, "Oh, nope, now you're getting colder." But the learning rate would be like the size of those steps. So if you made small learning rates or small changes, it would be like, oh, warmer, warmer, and you're just taking small steps to try to get it. You don't want to step past the thing you're looking for. And that's the idea is, how much do we want to adjust every time we're trying to figure out, what we need to change. So let's start by coding the activation gradient. And what the activation gradient is if you remember, we had the activation function here. We have going forward, we had ReLU, which is we basically want, if it's a negative number, we want just to return 0 or pass forward 0. And if it's above a positive number, it's above 0, we wanted to pass the number itself forward. Now, going backwards, we kind of want more of a binary situation where if the number is more than 0, we want the number 1. Otherwise, we want 0. So it's similar to how going forward we either wanted 0 or the value itself. In this case, we want 1 or 0. So if it was activated, we want a 1. If it wasn't activated, we want a 0. And the reason we want that is for the next step, but basically anything times 1 is itself, and then anything times 0 is 0. So it'll essentially null out things while going backwards. So we'll go ahead and do ReLU derivative, which again is, actually, hold on, let me type activation gradient. And we'll go ahead and pass through we're going to pass through the output. The reason we're passing through the output is we want the state of the output when we went forward, when we went through. You remember we got our output from ReLU, and then we moved it on, we pushed it forward. So as we work backwards, we still want that value. We want the original output that we gave, and then that way we can get that binary of ones and zeros of if we were activated or not when we went through forward. And in that case, we want the delta, or we want the change amount. So we're going to take that output gradient, and then we're going to multiply it by the activation gradient. And this is an in-place multiplication of 2 arrays. So what that means is we have our output gradient, which again was a shape of how wrong things were, the scores. And then we have the activation gradient, which is that, but either 1, where the value was activated, where it was a positive value, or 0, where it wasn't. So basically what it's going to do is by multiplying that, it's going to zero out anything that wasn't activated and just return the value in place of anything that was activated. Now there is a problem with ReLU. I mentioned that when we went forward, of the idea of if we're zeroing things out and we're turning off nodes, we may run into a problem. It's called like a dead neuron problem, where if ReLU deactivates a node and then we move forward, it won't reactivate and we won't consider it when we do backpropagation and so on, and it'll kind of just deactivate and just be sitting there. So there's a way around this, and we'll update the code at the end to do something using like a leaky ReLU. And the idea is that instead of 0, you give it a very small amount. So if it's the value and it's above 0, you'll give it, whatever the value was. But if it's below 0 or 0, you actually give it like a tiny bit of a value. So it still stays activated, but the actual impact of that node itself is not super valuable. So that if we do make a move at some point later in training, and with this small value where it's still activated, but it's not, it's not having an impact, if it does suddenly shift and is valuable, we can use that, but otherwise it's a small impact. So it kind of like gives you the best of both worlds. It leaves it open. So we'll update that later. But for now, we're just going to stick with ReLU, where it's either 1 or it's 0. It's either on or it's off. So the next thing we're going to do is we're going to compute the gradients for weight, bias, and input. Oh, I failed right there. Okay, so the first thing we'll go ahead and do is we want the weight gradient. And if you remember, in our within our layer, we have a set of weights, and these are the things between weight and bias. These are the things that we adjust for each node in the layer as we go forward and back to figure out, okay, we need to adjust this one a little bit more and it gets closer to the right answer and so on. So what we want to do is we want to take the scores from earlier of how right or wrong were we, and we're going to do some matrix multiplication based on these changes right here, or these deltas, these change amounts. So we'll do NP dot, which is matrix multiplication. And what we're going to do is we're going to take that delta, and then we're going to matrix multiply it by the transpose of the input. We'll circle back on what that means and why we're using the transpose of it, but it'll get into the shapes of the arrays themselves, and then the way matrix multiplication works. But the short answer is when you do matrix multiplication, the second dimension of the first shape, or the second dimension of the first thing you're multiplying, needs to match the first dimension of the second thing that you're multiplying. So in this case, the second dimension in delta needs to match the first dimension here. So we're flipping it. And what transpose means, and we can get more into this when we explain why we're transposing it, is you think of a like a table or like an Excel spreadsheet. You have rows and columns. It's going to flip the rows and columns. So the columns are now the rows and the rows are now the columns. So we have our weight gradient. So now we're going to do our bias gradient. And this one is a little bit easier. So the idea with the bias, if you remember, when we go forward, the biases, we're going to just need a number that we're going to move forward or backward on. So what we're going to do here is we're actually going to sum all of the values in delta on the first axis, and then we're going to keep the dimensions. We want to keep the dimensions, and we'll explain why after. And then what we want to end up doing is we'll get a sum of all of those, and the sum will be distributed across. So you'll see this after when we go ahead and update our weights and biases, but the biases and the weights will update based on this, and what the bias gradient will be the sum of all of the changes. So now we want our input gradient. And we're going to do another matrix multiplication here. And for this one, we want our weights. And then we're going to transpose that as well. And again, we'll get back to explaining why we needed to transpose it, but just remember transposing has shifts and rotates the columns and rows. So what the input gradient is going to do is we want to basically, this is what we're actually going to push forward. And the reason we're calling it the input gradient is, if you remember, we're working from the end result backwards through the neural network. So we're actually working from the end result and working our way back to the original values that we had. So by working backwards, you can see we're actually, like, as an input, getting the output, which is the output. Because it's coming from the next one, and since we're working back in what would have been the input of this one if we were going forward, we are going to pass that input gradient back out. And we'll get again into more of like what this math means in a second. But for now, let's go ahead and finish off this part. And then now let's update the weights and the biases. So the idea here is that within this class, this instance of the class, it is the layer, and it contains all of the nodes, and it contains the weights and the biases. So with this, we go forward with the weights we have in the instance, and on the way backwards, when we backpropagate, we're going to do the calculations and update those weights so that the next time we go forward, when we do another iteration for learning, we're going to use those new weights because again, they're a property within the class. And then we'll figure out how wrong we were, and then again we'll go backwards and update, and that just happens, a bunch of times depending on your parameters for training. So now what we're going to do is we're going to go ahead and update those. So what we'll do is this is where our learning rate comes into play. So we have our weight gradient. So you remember we did some matrix multiplication and we figured out based on our changes and everything, we now have a new amount of gradients or weights that we want to change. And what we're going to do is we're going to take our learning rate and we're going to subtract the learning rate times the weight gradient. And basically what we want to do is we just want to take whatever changes that we said we should make based on weight gradient and then use our learning rate to amplify. So if, again, it's a small learning rate, we want to just amplify by making a small multiplication. And if it's a big learning rate, it'll take whatever that weight gradient is and it'll multiply and it'll make them all very big. And then we'll do the same for biases. It's the same idea. We're going to take our learning rate and we're going to multiply it by the bias gradient. And then that's it for backward. Again, we'll come back and discuss this in a little bit. Now that we have our layer class coded, let's go ahead and code the model class. For this, we're going to go ahead and start and open a file. We'll just name it MLP.py, just something easy. And then from there, what we'll do is we'll go ahead and do class, and we'll just name it like MLP model. Doesn't really matter what we name it, but we'll just name it that. And then what we'll do is we'll go ahead and first we'll make our constructor. Oops. And we'll take a few different things. Since it's a class, we'll take self. We want the input size. So the input size here is as our neural network as a whole, how many inputs are we going to have? So in the case of like the MNIST data set, how it actually does it is it takes pixels of it. And so we actually have like an input size of, I believe it's like 780 something. But that'll be the input size. So it's the raw data that we're feeding into it. The output size is going to be equal to the number of choices that we possibly could have. So back to classifying handwritten digits, our input size is the pixels that are coming in of the images of an image rather, and then the output size would be 10. It's 0 through 9. So we have 10 options. So the output size, and then what we want to do is we want to make hidden layers. So the idea here is, and we'll put a default thing here. So the idea here is we have our input layer. So we have whatever the raw input is, and we have one layer that is the output layer, and that's like the 0 through 9 guesses. So what we want here is we want to put, and we'll actually make this a little bit, we'll make it hidden layer sizes. And what we can do here now is we would specify, say, the sizes of the layers in the middle of our neural network, the ones that are hidden. They're not directly seen by the calling code or the output. They're just kind of in the middle. And we'll just put something random. There's different philosophies and structures on how you can make your middle layers. So I'll put return there. So you can do like an hourglass shape where the first layers are higher, and then in the middle it like squeezes down, and then in the end layers it actually opens up to be more. You can do a funnel shape like here where you start big and then you go smaller. You can make them all the same size. And it just depends on the problem that you're trying to solve. For now, we're just going to make it a funnel shape. So next what we can do is we want to declare a class variable of layers. And we'll just make that an empty list or array for now. And then the next thing we want to do is we're going to make a layer sizes array, and this will be an array of the sizes of the layers themselves. And we'll use this in a second to actually figure out, to actually create our layers and so on. So first we're going to say we want the input size, because remember this is the first layer in it. It's going to be the input layer. And then we have our hidden layers. So we want to just put these here, hidden layer sizes. And we want now our output size. And if you're not familiar with this syntax right here, this would basically end up being like something along the lines of, it would evaluate to whatever your input size is, then the contents of our hidden layer sizes, and then whatever our output size is how it would evaluate to. So for now, we want to go ahead and create our layers. So what we can do is we can actually just loop through our input sizes. And what we'll do is we'll say I in range. So we want to loop through the layer sizes -1, because we laying -1, and then for each one in it, what we want to do is we have that self.layers, and we want to go ahead and append a dense layer. And this is where we made our layer class before. So let's go ahead and import that before we do anything. So we'll just say from dense layer import dense layer. So what we want to do is go ahead and make a new dense layer. And if you remember, the arguments for the constructor on the dense layer class was the input size and the output size. So the input size is going to be the current layer size. So we want layer sizes at I, and then the output size is going to be layer at output sizes +1. And this is the reason we subtracted 1 here from the range, so we didn't go all the way through, because for every layer, or sorry, for every output size, the layer is going to be an input of the current layer size and an output of the next layer size. And then we actually don't need to return anything here. That was just a placeholder. And then the next, we'll create the forward and backward functions. We won't actually fill them in just yet. We'll do both of them and just do return just so it's there. And then we'll do backward. We want the loss gradient, and I'll explain this in a second. And we want the learning rate. And we already discussed what the learning rate is, and it's the rate or how big of the steps we want to take, and how big do we want to adjust on each one. So the idea behind the forward and the backward is we saw that we have those on the layers themselves. So what the model is going to do is it's going to call the forward layer on the layer itself, get the output of that, then move to the next layer, and it's going to take the output of the forward of the layer we were just on, and it's going to pass it as an input of the next layer type of thing. So the idea is it would look something like this. And if you're wondering, I mentioned that it will take the output of the last layer and it will send it to the next one, and you're saying, well, what about the first layer? Well, that's where we have this, and that's where our input comes in. So the idea is that when we call our model dot forward to make an inference, what we're going to do is we're going to pass in the raw data of, say, our image, either a handwritten image or our Google Draw, the quick draw, the hand-drawn shapes and so on. So for the first one, it's what we pass in, and then for every one after that, it becomes the output of the last one. So how we're going to do that is we're going to iterate through all of the layers. And then for each one, we're going to say x equals layer dot forward. And then we're going to pass in the x. For layer. So the idea here is the first time around, we're going to call the first layer, and then we're going to call forward on it, and we're going to pass in the original x that came in. And then the output of that is going to overwrite x, so that when we loop back around and we go to the next layer to do the calculation, we take the output of the last layer, and it's now the input of the next layer. So every time, basically, it's overwriting x so that the next layer goes, that the x becomes the input and so on. And then when we return from it, we just want to return x. And the reason we want to return x is because after it goes all the way through all of the forwards, what we really want is to say what node, or we really want to say what does the last layer look like after going all the way forward. And because what we'll end up doing is we'll take, in the case of the handwritten digits that we're predicting the number of, the last layer will actually be an array of all of the nodes in that. So all of the possibilities, so we'll have 10 of them, we'll have 0 through 9, and it will be back to that scoring of how right or wrong were we. And ideally what it would look like is we have 0 through 9, and then one of them has like 0.9999 or 0.98, something very close to 1 to say, okay, this is, we think, the correct one. And then the rest are, 0.01, 0.001, so on. And then from there, we'll have some logic after in our inference logic to actually look at it and say, okay, which one is the highest probability and so on. And then we'll map that back to what our value is. So, and then the backward is going to be about the same. The only difference is that we're going to take our loss gradient. If you remember the output gradients when we're coding the backward function within the layer itself, that's going to be the loss gradient, and then the learning rate. We set this ahead of time when we go to run the training code. So for this one, it's going to be the same thing. We're going to say for layer in reversed, we're going to reverse the self.layers. And then for each one, our loss gradient is going to be equal to layer dot backward. And then we want loss gradient as the first one and learning rate as the second one. And we could probably name this like output gradient, just like we had talked about before, if we really wanted to. But really, well, we're calling it a loss gradient because it's, it's referred to as a loss. Like we're going to run some function or calculation to figure out how far away were we from the actual thing we wanted, and that'll give us that. So we're going to refer to it as a loss. And then for backward, we actually don't need to return anything from this because backward propagation, the backward pass, all we care about is updating the layer classes themselves. All we care about is updating the weights and the biases and so on. We don't actually need the output of it after running all the way through the backward. The next thing we'll do is code our loss function. And what a loss function is after we've made a prediction, we're going to take the actual output of what the value should be and our predicted output, and we're going to do a calculation of how different they are. And ideally, it will penalize guesses that are very wrong, more harsh, than ones that are just a little wrong. So to get started, let's go ahead and create a loss file. So loss.python. So the function we're going to be using is going to be mean squared error. And the idea is that when you square something, it will penalize larger numbers, or it will have an output of a larger number more for large numbers than for a small number. So the idea is, let's say you're just a little bit off. Let's say we're going to use whole numbers in this case. Know that it's not whole numbers, but let's say your difference between what you wanted and didn't want was, let's just give it like some arbitrary value of 2. Well, 2 squared is 4. So let's say the difference between actual and what you wanted has a loss of 4, or sorry, has a loss of 2. So you mean square it, and it's actually 4 would be the loss rather. But then let's say it's like 12 is the difference, and the actual loss value is actually going to be a decimal, and it's going to be on like an arbitrary scale, so it won't be whole numbers. But in this case, let's say 12 times 12 is 144. And then so on. Let's just take something in the middle. So like 6. That squared is 36. So you can see that the amount that it goes up is pretty steep. So things that are very far away will generate a very large number. And it's our way of, when we go back, kind of evaluating, was this, a little bit of an error or a lot of an error? So with that, we can go ahead and code that. For this, I think this is one of those things where there's some things that you want to code, and then there's some things where you want to understand the math, but the actual coding of it's not important. So I'm going to grab some code for this, and we will break down what it is, but we don't necessarily have to code this from scratch. So the math here is pretty easy. So for the loss, we basically want a float, which is a decimal, and it's going to take the length of our true value. So we just want basically, we're going to average. The mean is an average. So we're going to divide by how many total there are, and then we basically are going to square the actual value minus the predicted value for all these values. And what zip is it just basically makes a pairing of two values into one. So excuse me. So yeah, so what we basically just want to do is our true and then our predicted, and then we're going to, and then the derivative is a different formula. And just know that it's not necessarily important to memorize the math on this. It's just more important to understand the concept of a loss and the loss derivative. And the loss derivative is basically just saying, based on that, how much are we actually going to change the weights as we work back through. And if you remember from when we did activation, the main function was when we were going forward, and the derivative was when we were going back. With that, we can go ahead and start building our training logic. So what we'll do now is we'll go ahead and code our training logic. And the training logic is basically, we have this model, and it has all of these layers, and each layer has neurons, and each neuron has weights and biases, and it's the things that make it so that as we work through it, it does calculations and gets the correct answer. So what training is going to do is it's going to take our initial model that just has random values for both weights and biases. It's going to try to make a prediction, and it's going to look at the results, and it's going to say how correct or not correct am I, and then it's going to work its way backwards and go through each layer and each calculation to figure out, okay, where was I right, where was I wrong, let me adjust that, and if one was very right, it will make a small adjustment. It was very wrong, it'll make a large adjustment, and then anywhere in between. And then we're going to go and we're going to try again with our new weights and biases. And the idea is that with each one, we should get a little bit closer to what we want. And then the hope is that at the end of it, our prediction is correct. So with that, we'll start a new file called training.python.py. And what we'll do is we'll create a function, let's call it training. And then in here, we're going to need our model, and we're going to need X train and Y train. And what it is X is the input. So in the case of the MNIST hand-drawn data, it's the digits themselves, or the pixels from that. And then the Y is going to be the expected output. So what it would look like is, and X train and Y train, the reason it's separate is there's actually multiple. It's your whole training set. So what it's going to look like is the first value in X train and the first value in Y train are going to go with each other, and it's going to be X train first value is all of the inputs, first value of Y train is the expected output for that exact image, and then the second value of X train and the second value of Y train will go together, and it will be all of the, say, pixels as the input for, say, a handwritten digit 4, and Y train for that would be the number 4, and so on. And then, so next we need the number of epochs, and what this is going to be is it's going to be basically, I had mentioned that we're going to we're going to go run through all of the examples in our training set. We're going to make a prediction, make an adjustment, and then go on, and we're going to then say, okay, let's try again, but let's see if we're closer. And so the number of epochs is how many times do we run through our complete training data set. So we're going to run through all of them and then make some adjustments, go back, try again, run through all of them, and how many times do we do that? Now, I will say that there's another way to do this where we don't just straight say how many times do we want to go through it. There's a smarter way to do this where we actually give like a maximum number of times we want to do it, and we go through it until we've seen that we're not making progress anymore. So we might go through it, I don't know, 10 times, and then we see like, hey, 11th, we're not getting better, and we'll say, and there's a concept of patience where you say like, if I go 5 times, 5 epochs, and I haven't seen any increase, we're just going to take the best one that I've seen up until now. But we'll come back to that. We can always update this. For now, we're just going to say, hey, go 20 times or go however many times we want. And the learning rate is basically how big are those adjustments we're making. So we're going to make a prediction, see how correct or incorrect it is, and then we're going to use like the delta or a calculation between how correct it is and not correct, and we're going to use that to say, okay, I need to make an adjustment. And if you have a big learning rate, that adjustment is going to be multiplied by a big number, and if it's a small learning rate, it's going to be adjusted by a small number. And I should have a video on what learning rate means, so I'll link to that. And so what we're going to do now is we're going to go through all of the epochs we have. So we're going to say for epochs in range number of epochs, and that's to say we have 20 epochs, we just want to iterate through everything 20 times. And for every epoch, it's a fresh start. We're going to reset our loss. And remember, epoch isn't that we have 20, so let's say we have 10,000 data points in our training set. Epoch means we're going through all of those 20 times. So if you have 10,000, we're going to go through all of the 10,000, and that's one epoch. Then we're going to go through it again. So with each one, we've gone through a whole complete data set. So we actually want to reset loss to 0 because the loss that we're going to get is a new loss for this time through. And then what we're going to say is for x, y in zip, x train, y train. And what this does is, if you remember, I said that with X train and Y train, the 0 or the first value in X train and the first value of Y train go together, and then the second value in X train and the second value in Y train go together. So what this is going to do is it's going to take, and it's going to say, zip is going to, what zip is going to do is it's going to take, iterate through, and it's going to take, okay, the first value, and then that's X and Y. And it's going to go through again, and on the second time, it's going to say, okay, the second value of X train, second value of Y train, and that's going to be X and Y. So what we're going to do now, so basically what it's saying is for, let's say our epochs, we have 20 epochs. For 20 times, go through everything in the training set. So then we're going to reshape. Now I can explain why we need to do this, but essentially it's just reshaping the NumPy array so that if it's it's basically essentially reshaping the NumPy array so that even if it has a single value, it's an array. So even in our case of Y train, where say like the value is 7 because we expected the number 7, it's actually going to be an array with one element that has 7. And then next what we're going to do is we're going to want to go forward on this. And remember, forward is that making the prediction. So we're going to say model.forward. And if you remember, I said for x and y, it's going to be x train is the input values and y train is the output values or the expectation. So we're just going to go through x here. And I just realized I made a mistake here. And so what this should be after we go all the way forward is it should actually be the prediction that it thinks we should have. So the output should be, well, I say that what it is it's an array of loss values, or it's an array of values of what it thinks it should be, rather. So in the case of how we have the digits, we have 0, 1, 2, 3, blah, blah, blah. The output will actually be a thing that has a 0.0001 for 0, 0.012 for 1, and it's like basically values of the loss, or how correct or incorrect it thinks it is. So what we're going to do is we're going to correct the error. We're going to take that output and we're going to add. First, we'll start one thing. We're going to take the output and then we're going to, I just realized I need to import this. So let's go ahead and import. If you remember earlier, we made our loss function. So we're going to say from loss, import loss, and then we'll take the derivative to, I'll explain why we need that in a second. So first, let's just get the loss, and I'll explain why we're adding it to the loss in a second. So what we want is, what is the true value? And again, remember that is y, because for every input, we have the output, which is the expected or true output. And then we have the output of our predictions. And then, so now what we're going to do is we want to take this loss value and we want to calculate a loss, and we're going to add it to the loss. So the reason why we want to add it to the loss is what we're going to do later is we're going to take it and we're going to take it and we're going to average it out. So we're going to take this loss value that is a cumulative loss over all of the times you've gone through, and then we're going to divide it by the length of X train, or the number of samples that we have, because we want the average loss over all of them, because obviously some are going to be high, some are going to be low, but we want the average of all of them. So by adding them all together, taking whatever the loss is and then adding it to here, we can average it out later. And let's add some comments just to make sure things are making sense and we can kind of reference back to everything. So we're going to say forward loss. Okay, cool. So now we're going to go backward. And remember, what backward is that we've gone through, we've made a prediction, we've determined how incorrect or correct that prediction is. And then what we're going to do is we're going to use our model's backward function of that to go backward. So first we're going to get a gradient, like a gradient loss or a gradient output. So we're going to say, let's say gradient, I don't know, whatever. And then we're going to do this backwards of the first time, and I'll explain and what I mean by that in a second. And you saw here we went forward and then we fed the output of that into the loss function. We're going to go backwards and we're going to feed what we have now into the MSE loss derivative. And then we're going to go backwards through the model using the gradient we have and then the learning rate. And we'll stop over to those in a second. We'll refresh our minds on what the forward and backward do. But I want to explain why we did this first before going through here. So what we're going to do is we're going to take the loss derivative, and we should actually just go look at these for a second. And you don't necessarily need to understand the math or why this works or anything. We just want to figure out how much to change the weights based on our loss. And so what we want to do is we have an output right now. So we want to say like, okay, how much do we need to change it based on this? Or what is the gradient? And then we're going to go backwards with that. And so when you work backwards, you actually you're moving from the output to the input in the layer, if that makes sense. So you want to take what the output was, and then you want to take how much you should change it, and then you're going to pass that to the input. That was a long way that I don't think was super clear. We'll go back to the backward to make sense of this. But anyway, so we're going to take the learning rate, which is again how much do we want to amplify that change, or the change we need to make, and we're going to take the gradient, which is given that we've gone through everything, what's the gradient? And what the backward will do is we can go over here, and we'll go quickly through this. It's going to do the exact same thing. It's going to go through the layers in reverse using our loss gradient, and then we're going to pass that to backward, get the result of that, and then that result is going to be passed again backward to the layer before it. So we'll come back to that, and then from there we've now gone through all of our training samples and everything. And now what we want to do is we want to get our average loss, because I mentioned that we want to, how we are adding our MSE loss to the loss. So we want to take our loss and we want to divide it by the length of X train. And then we might as well go ahead and just print out what we have so we can make sense of it while we're training. And so let's actually put some comments in here. And then we're gonna round this just to make it easier. And we'll need to round it just because the actual value will be some decimal that could have like 100 different digits after the decimal point. So we just want to round it. So we're just going to say rounded equals round. Let's say average loss. I don't know. We'll say like 4 digits. It's fine. And then now let's go ahead and print it out. We'll say epoch, and what number are we on? We're on like epoch plus 1 because we're 0 indexed. And then we're going to say we're at that many out of num, oops, let's go here, num epochs. And then we're going to just print out whatever our loss is at the moment. And then we want it to, we'll just print it out. I was going to say we want to like round it, but it's already kind of doing that. So let's actually do rounded average loss here. And then yeah, that's it for training now. Go ahead and save that. So the next thing we'll need to go ahead and do is make the code to actually run our model. So we're going to make the code that actually runs the training logic and then after does the inference. So we'll just go ahead and create a new file called, we'll just call it like runner.python. And then from there, what we can do is we'll go ahead and we'll go ahead and create a few empty functions that we're going to need later, but we'll come back for those. So the first is we're going to actually need to be able to get our data set. So for that, we're just going to make one that's like get mnist dataset. And again, we'll come back for these just because I think they will make more sense if we fill them in once we actually get to that point in the code. And then the other one is going to be, we're going to need one called predict digit. And this will be for the MNIST data set for now. We can adjust this as well once we go back and do like say the Google Quick Draw where it's actually predicting pictures of say like hand-drawn rockets and mailboxes and so on. So for now, just know that we have a few things we're going to need from this. For MNIST dataset, we'll just fill in with comments like some pseudocode of what we are going to do it, or we are going to put in it, and then that way we're able to actually fill it in later. So the first thing we're going to say is we need to actually like download the dataset from somewhere. The second thing we're going to need to do is normalize dataset, and I'll explain what this is. We're going to need to encode the dataset. I'll explain this in a second. And then we're going to need to split our dataset into training and testing data. And then finally, we're just going to return the splits. So we'll go through what these mean. So we're going to download a data set just somewhere out on the internet. We're going to download them. And the data set isn't going to be perfectly what we need. So we're going to have to normalize our data set. And normalizing them just means we want pixel values to be kind of normalized to basically what we're going to do is they're going to be black and white images. And for every pixel value we get, we're going to divide it by 255 because we want basically some value of between 0 and 255. And then we're going to encode them. We're going to encode the outputs of them. And we're going to use something called one-hot encoding. And what that means is in our output, we'll have 10 things. We'll have 10 data slots. So it's going to be an array of 10. And we are only going to have one correct digit. So let's say it's back to the digit where we have a handwritten digit that's like, say, the number 7. And so we have 0, 1, 2, 3, 4, 5. So anything that's not a 7 is going to be 0. And then the correct one will be the number 1 to say, like, this is the exact one we want. And then let's say our data set has 50,000 samples in it. We want to take a small percentage of those and then use them to actually do the training and adjust our model. And then we're going to take the rest of them, and those are going to be ones that we can actually run our model against after to say, okay, how's it doing? Did it, we've trained it, but if it goes against data that it's never seen before, does it still correct it or correctly predict it? And then those splits, we're going to return the splits, and that'll look something like, well, actually, I can show you right here, but it'll look something like the X train and Y train, and then the X test, and then the Y test. So what we can do now is, and then for predicting the digit, this one is going to be a little bit easier, a little bit more straightforward. But predicting the digit is going to more or less look like this. We're going to take it and we're going to say, let's go here, we're going to say model and then X. And what we're going to do is we're going to say the output is equal to model dot forward, because remember we want to start and then we want to go forward with our input. And we're going to say reshape. We do need to reshape this. I'll come back to this to explain why we need to do this, because this will make more sense if we actually print the values out before and after the reshape. But we're just going to run through all of it. Basically, the way we predict it, you remember during our training, what we did was we would say like, okay, I have this, let me go forward through the model and I want to get what it thinks it is, and we'll use those to go backward. In this case, our model should be in the state that we want it to be correctly predicting. So we're just going to go through it forward once from the start node to the end node, and we'll get the output. And then we're going to need to say return np.argmax of the output. Oh, and let's actually, while we're doing that, let's go ahead and import NumPy. NP. And the reason for the argmax is when we actually get our outputs, we want, if you remember when we were doing the training, we want the value out of all of them that is the highest. So It's going to say one might have like 0.999999, another one point like 0.1, and so on. And we want the highest one because that's the percent chance that it thinks that it is this value. So we're just going to return that. And now what we're going to do is we're going to go ahead and we filled in this one. We'll come back to fill in the getting the data set. So what we're going to do now is we're going to create our model. And then that's going to be, let's go ahead and actually import that. So from, what do we name it? MLP, yeah, MLP import, what do we name it? MLP model. Okay. And we're going to name it, do equals MLP model. We're going to make a new one. And then we see here we have the input size, the output size, and then the hidden layer sizes. So in a neural network, the first layer will always be the number of inputs. So in the case of the MNIST dataset or the Google QuickDraw dataset as well, it's actually every pixel is going to be an input. So we'll actually have, I believe, 784 because it's like a 72 or 74 by 74. So it ends up being every pixel is an input. And then we want our output size. And in the case of the MNIST dataset, we have 0, 1, 2, 3, basically all the digits 0 and then 1 through 9. So we have 10 for output size. And then the hidden layer sizes, so we have an input layer and we have an output layer, and we can have any number of layers in between. This becomes one of the things that we can tweak if we're not getting the results we want. We can either change the shape of the layers. So this would be, in this case, we would have 3 layers in the middle, and the first one would have 256 nodes, the second one would have 128, the third one would have 64, and this is known as like a funnel shape. We also have like hourglass shapes where, you know, it goes like a big number and then a smaller number and then back to the big number. You can also do them all the same sizes. Different shapes work for different things. And then you also could just add more layers into the mix and so on. So it ends up being one of those things. It's a pros and cons thing. I'm going to use this default here, but I'm going to type it in just because I think it'll be helpful for us to see it as we go. Because if we need to, you know, if it's just maybe not working out and we need to adjust it, we can go ahead and do that. So now we have our model and we can go ahead and start training our data. So let's go ahead and let's go from training, import training. And then now that we have our model, we can go ahead and we actually need to do one other thing before we do that. I had mentioned that we created this MNIST dataset. We actually do need to do one other thing. We actually have to get the things to pass in. Because if you remember when we went training, we have X train and then Y train. So we're going to actually, for now, we'll delete that. And we're going to pull from get MNIST dataset. And we're going to say, and again, I know that MNIST dataset's not filled in, but we'll go ahead and fill that in a second. Test Y train Y. Test. That's going to be equal to get MNIST dataset. And then just remember, we need to go fill this back in. So then what we're going to do is we're going to call back to our training, and then we're going to pass in our model because we have that. We have our model class here. And then we're going to pass in X train, and we're going to pass in Y train. And if you remember, X train is the inputs and Y train is the predicted outputs. So for, say, it'll give all the pixels for a handwritten digit that looks like a 4. And then the output of that will be an array where it has like a NumPy array where the 4, the output for the 4, hopefully, should be the highest. And we'll see when we go in here, we're going to use one hot encoding. So in our case, everything will be 0, and then the number 4 in there will be 1, meaning like this for sure is the number. We talked about epochs earlier, so we're just going to put 20. And then we talked about learning rate. You could go as high or as low as you want. This is one of those things you're going to have to mess with. So we can get an idea of how this is performing. We're going to take big steps. We're going to put our learning rate kind of high. And then at this point, after this, our model class here should go through everything, and then our model class should be configured so all the weights and biases are correct to predict. And it's passed by reference, so we're not returning it here, but inside of this training thing, it is actually modifying the class itself, or the object itself rather. So then right here, what we're going to do is we're going to actually run through we're going to take our new model and we're going to run through and do the run through some of the test data, and not the training data, but the test data itself. So this should be data that we've never seen. And just for the sake of this video, I'm just going to run through the first, I don't know, 10 examples on that. Oh, whoops, I in range 10. And then what we're going to do is we're going to say x equals x test I. We basically just want the ith value in the x, and then y true. So this is the true value. We're going to do np, so NumPy array.argmax. Because if you remember, so let's do this for y test I to the ith value in the outputs. And what argmax does is, so for what our outputs are actually going to look like something. So 0 through 10 is going to be like, let's say our value that we want is 4. So it's going to be like 1, 2, 3, and maybe 1, 6, 7, 8, 9. So what it's actually going to do is, this is what this predicted value, or the true value, is actually going to look like. It's going to say 0% chance it's 0, 1, 2, 3. 1 or 100% chance it's 4, and then 0% chance it's any of these. When we do our predictions, it won't be like this clean. It'll actually be like 0.999999 and so on. But anyways, so what we want to do is we want to take the max, the index of the max. And then, so now what we're going to do is we're actually going to predict. So we're going to say our prediction is equal to predict digit, and we're going to pass in our model. And then now we're going to pass in our x, which remember was this right here. And then we should have a prediction now where we can say, okay, let's print the actual, and let's print the predicted. And what it'll be is it'll be like y true. So this is the one that we know that's correct, and then we can do our predicted. And just since we're doing y and y, let's go ahead and just add like y prediction, just to make it that. And then, so now what we have, minus that we still have to fill in the getting of the data set, we have create a model, get our data, train our model, and then for the first 10 in our test data set, go ahead and predict the digit, get the output, and then we're going to check against how it is. All right, so let's go ahead and run this now. Let's go terminal. Let's do a conda activate. I think I have one that's like trading or something. Okay, perfect. Just so I don't have to, I have a conda environment that already has all this stuff installed. And now what we're going to do is let's go to runner. So we want Python 3 runner, and let's see what goes wrong, or if it works, or how this goes. I probably should have put some printing here. Let me do that just because I want to make sure that we're not getting stuck. Let me just put something here like print downloading mnist. I just want to make sure. And let's say print before training. Oh, sure. Before model creation, then before model training, and then that should be good. And then we'll get stuff here, so we're not that worried about it. So we'll hit that, and then let's go clear, and then let's go ahead and try to rerun this. Okay, cool. That's actually what I wanted. It's weird that it said before model creation, and then it downloaded. Oh, that's right, because we did that. Okay, cool. Before model training, and then I bet we didn't print out anything in here. Oh, we did here. So it would be nice if we would have put some stuff up here, but for now, let's just see if anything prints out. We should have probably did this more, or used like, I think it's like TDQM or TQDM will give you like a little progress bar as you work through things. But let's see what happens. All right, cool. So we got our first one, and we see our loss is 0.6 is the average. So ideally on our second one, we get a little bit better. It's possible that we get a little worse though. With training on each epoch, it's not linear. Like you don't always get a little bit better. So it might get worse for one or two and then get much better. So it might be that, or sometimes it just gets better on each one. So let's see how it goes. Yeah, see, we did get a little bit better. So we'll see. I'm kind of regretting trying 20 epochs though, so let's actually take a step back and we'll go back to our runner. And let's just do like 10. And I'll also speed up the video during training so we can also like fly straight past that. But we'll only do 10 just so it can go ahead. So now that we've got some results, and they are results, but they're not great. It's really good about 7s, but nothing else. We can kind of dig into why these aren't working. So what we can do is we can go back to our training. And I had mentioned earlier that there's kind of a better way to do training versus just using epochs themselves, but to actually make it so it's a little bit more dynamic. So one of the things we can do is instead of epochs, we're going to switch this to max epochs. And then what we'll do is we'll go ahead there. Because now what we're going to do is we're gonna go as long as we need until we get a good result. So the next thing we can do is we're also going to define something called patience. And what this means is we can see with our results here, we would have a bad one, we'd maybe get a little bit better, a little bit better, a little bit better, and then it would actually regress a little bit and get a little bit worse, and then a little bit worse. But then after a few of them, it would get a little bit better. And that's expected. And then we'd get a little bit worse, and then we'd get better overall. So what's going to happen is it's going to kind of keep doing that back and forth, hopefully working towards the right direction. But at some point, it's going to stop getting better. It's just going to get worse. So what patience is we'll set it to 5. What patience is the idea that instead of defining how many epochs we do up front, we're just going to keep running until we get better. And every time we get a little worse, we're going to say, okay, we've gotten worse for 1 now. Okay, we've gotten worse for 2 now. And then if that happens for 5, we just say like, this is about as good as we're going to get, or whatever our patience number is here. But then if we get worse for 2, but then we get better, okay, we're going to start over. Our patience is at 1. But then we got a little bit worse. Okay, patience is at 1. We've gotten bad for 1. And then we get a little bit better, so it resets to 0. The idea is we're not going to stop it before it's ready, but we want to make sure that it doesn't go too long, that it's continuously getting worse. So what we can do here is we have our loss here, and we're going to actually define a best loss equal to 0. And then we'll want our best model, because what's going to happen is every time we hit the best version, actually what we can do is let's just make a deep copy of the version we have. I say copy.deepCopy model. Let's go ahead and import that in too. So just realized I should probably import copy. Cool. So first thing we're going to do, we're going to take the best version of the model. I just realized I named it model. And we're going to make a copy of it to start. And every time we hit the best we've ever seen, we're going to copy whatever version of the model class we have into this one, the instance rather. So then what we can do now is, so we got this, best loss, that, oh, I just realized we actually want this to be at high number. We don't want it to be, so we're going to make it infinity, basically as high as it will go, because if the best loss is, if we start at 0, 0 is just always going to be the best loss. It'll never get better than that. So there's that. So loss, we're actually going to start, so loss is here. Oh, I just realized something. We want to, oops, actually I want these to be, independent of the epochs. So, and then we'll also do our patience counter. So patience counter 0. So basically, if we ever reach that value, ever reaches 5, we know that we've seen the best we're going to get, at least for now. We can adjust that to higher or lower, whatever we want, and then we can stop. So for the most part, everything else is going to be about the same. The only difference is when we get down, so we've got our epoch, blah, blah, epoch and epochs. Yeah, so when we get to about right here, we're going to say if, let's do this. So we have our average loss, and then we want to say our best loss. So if our average loss is less than, or actually, sorry, if our current average loss is better than our rounded, so we got a rounded best loss. Oh, best loss. We just named it best. I was going to say rounded best loss, but we just named it best loss. If our average loss is less than our best loss, that means we have a good one. So now we're going to say our best loss is now equal to our average loss. And then we're going to say our patience counter is back to 0, because remember, we've hit a good one, so we want to reset that. We're going to make a copy of our best model. So our current model is going to be copy.deepCopy of model. And then I think that's it for now. And if it doesn't, just go ahead and increase our patience counter. So we're going to increment it by 1. Other than that, I think everything should be good. The only other thing we're going to want is we're going to want to go ahead and do this. We're going to go ahead and make it so if our patience counter is more than or equal to the amount of patience we want, then we're just going to print like stopping early, hit patience. And then we're going to break. And then I think I had it earlier, so it was just not returning the model. I'm actually starting to think like best model equals best model. Why does it say not accessible? Oh, I see. Let's move this. Let's return best model. So before it was just like making alterations to the model. At this point, what we actually want to do is we're going to change it so we're returning the model because whatever, regardless of what happens to this model class, we only want this best one. Because remember, based on the patients, we could see our best one, and then it could get worse for like up to 5 times or however long this is. So we don't want that one that's a little worse. We want the better one. So we're going to do that. And then now what we'll do is, where's our runner? We're going to go, I'm actually going to say model equals, and we could have done this before. It would have been fine, just return model, but we're just, now we actually need to, because we need for sure the best one. So I'm going to say model, blah, blah, blah. And then remember our max epochs, oh shoot, sorry, learning rate, we're going to say patients equals 5. And then we're going to make our max epochs equal to, I don't know, let's make it something crazy. Let's make it like 100 or something like 100. It should stop before this. If it doesn't, it means that we need to go. But if we're running into problems where we're at this many epochs and it's not correctly identifying it, we probably need to make some other alterations. So we'll just set it at 100. And then yeah, so now we'll go ahead and run it. And instead of it just running 10, it should just run as much as it wants. Let's do one other thing too. I want to go back to training, and let's make a note that the let's print whenever it says like say and then we'll just make this, and then we'll actually print our that through that. And we're just gonna put epoch. We don't care about the max epochs because we're that. What we do want to do though is let's go down here, and we're actually going to move it down here because what we do want is we want to know what is our patients count at. So we're going to say patients counter, and then we'll do like patients. So we'll say like, okay, we're at 0 out of 1, blah, 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 blah. So we'll do that. And I think that's good. I think we're good here. Let's go ahead and try this out, and we'll see how it goes. So blah, blah, blah. So we went through that. Okay, I think we're in a good shape. Let's go ahead and run this. And what I'll do is I'm going to move this to a different window, and I'm going to move it to a different, so it might get shaped weird, but I'm going to move it to a different window just so I can move it out of the way because it's probably going to run for a while. So please hold. So I realized right after I recorded this that I didn't have my microphone on. But what I'm basically going over here is just showing a few things that I adjusted. So I did move down the learning rate to 0.1. I upped the patience to 10. I kept the max epochs at 100. And then in a second, I'll actually scroll down in this portion of the video and show you where you can see why the patience is important, where there's a few sections where it actually, you can see that it would bump up a few, the patient's count would bump up a few, and then it would go down. And then you can see actually towards the end where it actually started, you could see it was patients' numbers were climbing more frequently. And then at this point, it ended around 88. And then the result after this was that if you once I scroll down, you'll be able to see that it correctly predicted everything. And here you can see I scroll down and everything's correctly predicted.